And then I moved here to Wisconsin, and then last year we were looking for a senior person again to hire. And again, very, very excited that Debdeep moved here now from Texas A&M University and is in his first year here. His research, broadly speaking, is on understanding statistical and computational trade-offs for probabilistic inference in complex models. And today he's going to tell us about variational. Debdeep, the floor is yours.
Matthias, for the very nice introduction, and thanks for the kind invitation. So I had actually given this talk or version of this talk last year at the Department of Statistics. So my apologies if the stat folks have a very good memory of it. The talk today will be primarily based on some of our recent understanding of variational inference, which has become an increasingly popular scalable alternative to Markov chain Monte Carlo for fitting complex Bayesian models. So despite the empirical success, there has been somewhat of a limited understanding of how the method performs theoretically, and that's going to be the main focus of the talk today. So I'll also highlight a couple of key examples where apparently very innocuous choices of variational family can lead to misleading inferences, and we'll provide some remedies. And those could be useful from a practitioner's point of view. Okay. So I'll jump right into the notations. So I'll denote Y superscript n to be the set of all observables. And the set of all hidden variables is denoted by W superscript n, which includes the parameter of interest theta and the vector of latent variables z1 through zn. So we then postulate a statistical model by first prescribing the observed data likelihood, which is the conditional distribution of your observables given the latent variables and the parameter of interest, and then prescribing the latent variable distribution given the parameters, and finally a Bayesian would conduct inference by placing a prior distribution on the unknown parameters theta. All the inference would be based on the joint posterior distribution on the parameters and the latent variables given by the Bayes formula. So much of the problems that we see in Bayesian computation or in general approximate Bayesian methods stem from the intractability of the normalizing constant, which is difficult to obtain beyond very simple settings or in low-dimensional problems where it's actually possible to numerically integrate. Okay. So of course, Markov chain Monte Carlo has been coming to our rescue for the last 30, 40 years or so that can actually avoid computing the denominator and still generate samples from the posterior distribution. But with the advent of more and more complex data, there has been some issues with applying MCMC. It's fair to say that one requires a lot more care and tuning to guarantee the performance of MCMC. So there has been a parallel development in approximate Bayesian computation methods, starting out with Laplace approximation in the late 50s, and then moving on to more structured inference towards the beginning of this century, under the general umbrella of belief propagation that includes expectation propagation and VI as a special case. So I'll focus primarily on variational inference, which instead of drawing samples from the posterior, aims to approximate the posterior from a tractable class of probability distribution in the sense of Kullback-Leibler divergence. So assuming that we can solve this minimization problem, let's define Q hat Wn to be the minimizing point of the posterior within this tractable family of probability distributions. Now, why this method is able to bypass having to compute the normalizing constant? So this can be seen readily from this following identity. You can actually write the log marginal probability of the data as a sum of two quantities for any given probability measure Q. The first term here is the KL divergence between Q and the posterior, and the second term is what we are going to call as the evidence lower bound, because log probability density is called evidence in machine learning literature, and since the KL divergence is positive, the second term actually serves as a lower bound to the log marginal probability. And since the second term is free of any normalizing constant, minimizing the KL divergence is equivalent to maximizing the evidence lower bound, and thereby the variational inference can avoid having to compute the normalizing constant. So of course, the success of the variational inference methods depend primarily on the choice of variational family. One of the very commonly used families is the mean field variation family, which assumes that the distribution on theta, which is d-dimensional, to factor into individual marginals. Of course, this family is popular not because that it's a very good approximating class, but because one can optimize the KL divergence over this space quite easily. More specifically, one can actually run a coordinate ascent algorithm by updating one variable at a time, fixing the remaining variables. And in doing so, each of the subproblems are convex. And even more, by exploiting the tensorialization property of KL divergence, one can explicitly write down the update of the jth coordinate in terms of the other coordinates. So one can think about other variational families, for instance, restricting it to members in the exponential family. More expressive variational families are also very popular nowadays, starting with the normalizing flows, black box variational inference, implicit variation. So what are the key questions of interest? Of course, we want to know whether the optimizer that we're getting at the end of the day is a good proxy. In other words, whether Q hat theta inherits all the nice properties of the posterior distribution. From the computational side of things, we like to answer whether the optimization problem involved, which is often non-convex, leads to the global optima or not. And this has been actually answered in very special cases until more recently. But we are going to talk about a general theoretical framework to analyze the computational algorithm associated with, say, mean field inference. All right, so what can we actually expect? So of course, if we do not have a very expressive family, let's say we are just working with the mean field family, we can't really expect to capture all aspects of the posterior distribution, right? So let's say we are trying to estimate a posterior distribution, which has a very complicated contour by just the mean field family, then what we can actually expect is that probably the mean or median of the variational family to align closely with the mean or median of the posterior, not the entire posterior distribution. Okay. So in a sense, there would be a loss in estimating the uncertainty. But variational inference is primarily used traditionally for rapidly obtaining point estimates. And we are going to answer whether there is any statistical loss in terms of convergence rates if you apply variational inference. So for non-identifiable problems, VI is often used for model selection. For instance, the evidence lower bound that you get as a byproduct of variational inference is sometimes used as a surrogate for the marginal likelihood, which is often used for model selection. And we would like to answer whether the elbow is a good surrogate for the marginal likelihood. Okay. From the computational side of things, we'd like to answer questions like whether initialization plays a role here. How does the algorithmic convergence rate scale with the dimensions and so on? Second, feel free to stop me at any point of time if you have any questions. So before going into the theory, I'll start with three specific examples with a mix of both positive and negative results. So I'll start with a positive, which is an illustration of variational inference in the case of sparse regression. So this is a very commonly used example. So let's say we are working with a high-dimensional linear regression model with Gaussian errors with variance sigma square. And we assume sparsity in beta. So natural prior distribution that encourages sparsity is the spike and slap prior, with an overwhelmingly large probability, we set beta j to 0, and with remaining probability is drawn from some distribution, which we call a slap distribution. And we are just going to focus on normal here. So if you look at the posterior distribution from this likelihood and the spike and slap prior, the posterior is actually intractable in the sense that it's a sum over, so the normalizing constant is a sum over 2 to the power d many terms. So it makes sense to apply variational inference here. So we simply use the mean field variational family to approximate the posterior, which assumes independence of the beta j's. And
yeah, just a clarification. Yeah. Is there any reason why you're putting so much weight on essentially beta having maybe 1 or 2 non-zero entries? Like, why is it this 1 over d?
So yeah, I mean, it's typically the right choice if you have the sparsity over the sample size going to 0, an assumption. Yeah. So let's work with this mean field family and look at some illustration.
If I just took a Gaussian prior, right, then clearly the posterior will not be diagonalizable like this. So this is, but it's simple, and you're going to show that somehow it still delivers in cases of interest, even though in the simplest setting we can already see it's never going to work.
Right.
Perfectly. Yeah.
Of course, you can't never recover the posterior to better. But as a point estimate, can we say something about it? Okay, so here is a illustration of how the variational inference works. So we are running coordinate ascent, and we initialize all the variables at, let's say, point. So the red line is the variational estimate, and the black dots here are the true values of the regression coefficients. So the first 5 of them are non-zero, and the remaining 195 of them are exactly 0. So this is the iteration 2. We start seeing some convergence, and then iteration 3, by iteration 4, things are nicely converged, and it doesn't move from that particular place. And we can see that the convergence is reasonable, at least by eyeballing. But we want to kind of make sure whether statistically there is still a difference between the red dots and the black dots. So we'll come back to this example, but let's look at another example where we do not have a positive result. So this is a linear Gaussian state space model, fairly well used in econometrics. So we have an observation model, which is Gaussian, conditioned on latent variable z. And we have an evolution for the latent variable, which is an AR1 process. So the parameters here are the regression coefficients, A, B, and the variance parameters sigma h squared and sigma b squared. And of course, the latent variables themselves are known parameters. So we place a standard Gaussian prior and inverse gamma prior on the regression coefficients and the variance parameters. Since the posterior is intractable in this example, let's work with a mean field family, which is a complete mean field over all the latent variables. And then we are assuming distribution on theta. So we are not in field across the coordinates of theta, although in principle you can do that. So clearly, this mean field ignores some dependent structure that is present in the data generation mechanism, right? Now you can prove something like this. If the true autoregressive coefficient is bounded below by 0, then the variational estimator is actually inconsistent in this example. So of course, ignoring the dependence leads to some price here, not in the previous example.
So just to clarify, your theta is multiple parameters.
Right.
Is it just that like our estimate of A is messed up, or is it actually all of them? That I guess I'm just curious what the norm is.
Right. Yeah. So here we are just working with Euclidean norm. I think what we have seen, all the parameters are messed up to some degree.
Okay.
Okay. So let's move on to another example where things are not identifiable, but we can still use the evidence lower bound as a surrogate for the marginal likelihood. Okay, so we have observations y1 through yn, and here we are interested in selecting between k models. So what exactly a model means in the context of Bayes inference? A model is simply a collection of a prior on your parameter and a likelihood. So we have k choices of this likelihood prior combination, and a standard way to select between different models would be to look at the marginal likelihoods for these different models and choose the one with highest order. Then the marginal likelihood appears as a normalizing constant of the posterior. That's the very reason we started out with variational inference. So this is typically difficult to obtain, again, beyond simple settings. So we often use expansions, higher order expansions of the log marginal likelihood to approximate the log. So one such approximation is the Laplace approximation, which expands the log marginal likelihood around the maximum likelihood estimator, assuming its existence, of course. And then if you simply do a Taylor expansion, the first order term vanishes, and the second order term reduces to a Gaussian integral, and that delivers a penalty in the dimension, is known as the BIC penalty, in the form of d over 2 log n, and the remainder is all higher order terms. Now you can only do this for certain kind of models, which are called regular, meaning that if you look at the KL divergence between the true data generating density and the model that you are fitting, that's actually minimized at a singleton, not at a multiple points. And the Hessian matrix of the log likelihood is positive definite around that particular. And this actually allows you to expand the log marginal likelihood and come up with this particular expansion. So, of course, in many models that we see, for instance, mixture models, factor models, hidden Markov models, reduced rank regression neural networks, we do not have regularity. So what we do in such a scenario? So there is a very nice sequence of articles, which is actually summarized in this book by Sumio Watanabe. That showed that in singular settings, singular means if your Fisher information matrix is singular at that particular point of MLE, at the true value, then a different expansion of the log marginal likelihood is valid. Okay. So what is the expansion? So the first term is the log likelihood evaluated at the true data generating parameter. And instead of d over 2 log n, you have lambda log n. Okay? And then you have a higher order term, which is m minus 1 log n. And then there are some OP1 quantity. Please go ahead.
Why is that m in front of inside of the log in front of the y to the n? Why is that?
The log n term?
Or the m in front of the y to the n?
It's not super important, but still, if you want to really approximate the log marginal likelihood well, in some cases, you can see two models can differ in their m, but not in their lambda. So it can still detect between those two models, actually. Yeah. So this lambda and m, these are called the real log canonical threshold and multiplicity associated with lambda. And the typical range for lambda is between 0 and d over 2, and m is between 1 and d. M is an integer. So you can see the Laplace approximation corresponds to lambda being d over 2 and m being exactly 1. Okay?
Yeah, Debdeep, I think the confusion was about the m being used on the left-hand side to denote the marginal likelihood, and then there's a different.
Oh, I'm sorry. Yeah.
Yeah.
Right. So
different things.
So MYN is the marginal distribution of the data. I should have written FYN. That's the notation that I started. Yeah. Thanks for clarifying. Okay, so lambda equals d over 2 and m equals 1 corresponds to the usual Laplace approximation. And there are many examples in this particular book of singular models like reduced rank regression, where you have a lambda which is strictly less than d over 2. It's typically quite hard to find these numbers, lambda and m, for a given singular model. Requires some algebraic geometry tools to solve for these two numbers.
So just to see this lambda and m, like the multiplicity of this threshold, these are really just functions.
Right. So in some sense, theta star has some role to play here as well. So if you change theta star, you'll get different lambdas.
I see.
In some cases, if you generate a, let's say, if you're fitting mixture of two normals, and your true data genetic distribution is just one normal, so you can achieve that one normal by several combination of these parameters, right? So then lambda would be strictly less than d over 2. But if you start with a mixture of two normals itself, then you get lambda to be exact. Okay, so let's look at a very simple example. So we have a nonlinear regression model where the regression function is a quadratic function in x, and the distribution of x is uniform -1 to 1. So the regression function is actually a times s of bx plus cx. And as you can see, there are three parameters, a, b, and c. Now, when the true parameter is 0, 0, 0, then you can find the tail divergence. And that actually becomes 1/2 ab plus c whole square plus 1/6 of s squared b to the 4th. I can see that if we set A and C to be 0, regardless of the choice of the scale divergence would be 0, right? So the scale divergence is 0 for a continuum of points, not just for a single value. And in this particular case, lambda is 3/4 and m is 1. So there are three parameters. PIC would tell you lambda is 3/2, but it's not exactly. Okay, so now let's see what we can do with variational inference here. So we are interested in the posterior of A, B, and C. So we assume a mean field family, and we run the variational inference. We get evidence normal. And if you do so, the estimate that we obtain is around -1 in front of log n, where it should be 3/4 in front of log n, right? So Laplace approximation is giving a wrong result that we know because this is not an identifiable model. And there is a discordance between what the singular theory tells you, which is 3/4, and the mean field inference. So how do we actually correct for it? So that's going to be the main question. So we'll start with the easy case where things are identifiable. So we have a true data generating parameter theta star. And let's say we are interested in delivering risk bounds for the variational estimate, meaning that using a statistical distance d, we want to upper bound the risk associated with the variational estimate Q hat, and a standard benchmark to compare this risk against is the minimax rate for this particular problem. If we can show that this risk is upper bounded by the squared minimax rate for that particular problem, then we know that at least the mean for the variational estimate is doing the right job. Okay. So what are the key requirements in making sure that your variational inference is doing the right job? So right now we are not in the mean field family, but we are looking at variational inference in general. And then we'll specialize to the mean field once we look at a few examples. So here is the true posterior distribution. So of course, the key requirement would be the posterior itself should be optimal. Otherwise, it doesn't really make sense to have the variational inference to do the right thing, right? So we want the posterior itself to concentrate around this pseudo-true parameter theta star. And fortunately, this problem is well studied in the literature. And there is a very nice book that lists sufficient conditions for the posterior to concentrate well around theta star. So on a high level, the assumptions are the following. So the model should be identifiable in the parameter theta, and the prior should assign enough mass around the true parameter theta star. So can we actually use these ideas to say something about the variational estimator? So recall that a variational estimator is actually trying to minimize the negative elbow, which can be written as a combination of two terms. So the first term can be thought of as negative of model fit, which is the log likelihood ratio, integrated with respect to the variational distribution. And the second term, which is the KL divergence between the variational distribution Q and the prior pi, is sort of regarded as the penalty parameter. So this is the kind of the main result that we can come up with. If h squared denotes the squared Hellinger distance between the model and the true deteriorating distribution, then under some model identifiability conditions with high probability, you can bound the Hellinger risk by the minimum variational risk plus some smaller order quantity. But why this is useful? Because since this is the minimum risk, we can actually substitute Q to be anything, and that would serve as an upper bound for this variational risk. So now we don't really want to substitute anything here. We want the bound to be tied, and we know that the variational objective function is minimized at the posterior itself, but we can't really plug in the posterior to make sure that the bound is tied, because we don't really know the posterior. But we can actually plug in a surrogate for the posterior, and this is actually the theoretical game that we have to play for each example that we try. So this surrogate is the following. So you simply restrict your prior to small Kullback-Leibler neighborhood around the true parameter, and the neighborhood size is delta. And by tuning this delta, you can balance between the model fit term and the penalty parameter. Okay? And it turns out that if you choose delta in a way, you balance the model fit and the penalty, this leads to optimal rate for many statistical problems we care about. Okay? And let's look at an example. So going back to the high dimensional sparse linear regression, if we start with some sparsity assumption and some assumption on identifiability of the model, like the sparse singular value assumption, we know that the posterior is optimal. And under the same assumption, we can actually show that the variational optimizer under the mean field family is also minimax out. So now going back to the linear Gaussian state space model, we don't really assume mean field across all the latent variables, but we assume that there is a joint distribution in the latent variable. But the distribution of z and theta are independent in the variational family. So of course, you can't use coordinate ascent to update your parameters. If you assume a joint distribution, you have to use forward-backward filtering to do so. So you have to pay a price in terms of computation, but statistically, you will get the optimal risk for the variational estimate. So you include a little bit of dependence in the latent variables, and that would result in the right behavior of the variational distribution. So now let's come back to the third example, which is structured inference in singular models. We already saw that if you use the mean field directly on the singular model, then there is no way you can get the correct value or correct expansion of the evidence lower bound. But it turns out every singular model can be reduced to something called the normal form, which pretty much means that you can map the points of the singularity in the singular model to zeros of certain monomial. And if you use such a transformation to the singular model, it's possible to reduce the marginal likelihood in this very simple form where we have e power a monomial times another monomial. Still, there is quite a bit of dependence between the variables phi1 to phi d, which is in the likelihood. But if you use mean field on these transformed coordinates, surprisingly, you get the -3/4, which is the right order that you get out of the singular model theory. And the updates are fairly easy. If you the coordinate ascent updates, you can write down fairly easy if you assume a normal form. But I'd like to show you this particular picture. So this is the variational optimizer using mean field. And this is the target. They are very, very far apart, right? Of course, you're assuming mean field, and there is a huge dependence between the psi parameters. But fortunately, if you integrate these two, they are of the same order, which is, I think, quite surprising. And you can prove this, that if you use mean field on the resolved coordinates, the elbow is of the order lambda log n. So you pay a price, of course. You can't get anything, everything for free. So pay a price on the log n term. But at least you recovered the leading term. So this is all based on the idea that you have access to the transformation, and you can reduce a very complicated singular model, let's say a reduced rank regression or a neural network model in this normal form, which is often quite hard to obtain. It turns out you can actually learn the transformation under some conditions. So if you consider a slightly more expressive variational family by pushing forward your mean field onto the space of the transformation and learn the set of all transformation using normalizing flows, you get back the same result. So I'm actually putting some conditions here under the carpet. And so it requires this mapping to be invertible. In general, they are not. The mapping between a singular model to the normal form, they are not always invertible, but in some cases, you can actually construct invertible maps. Anyway, so just to conclude the first part of the talk, so what are the recipes to ensure that the variational family is doing the right thing? Okay? First of all, you have to make sure that your likelihood and prior such that the posterior is optimal. That's the most important requirement. Regarding the variational family, what you need to ensure is that your family should have densities of this particular form. Right? So this is prior truncated to small scale neighborhoods around the two parameters. So what does it really mean in the sense of approximating using mean field densities? So typically, if there is a high correlation between variables, this neighborhood, the KL neighborhood, would not be rectangular. This should be ellipsoid, right? And what you're doing really, you are trying to approximate the volume of a hyperellipsoid using the volume of a hyperrectangle. If you're trying to approximate, let's say, highly correlated density with mean field. Now, you know that this is not possible if the dimension goes to infinity because of escape of mass, and that's exactly what's for the linear Gaussian state space model. But if it turns out that the dimension of your latent variables is not growing to infinity, unlike the state space model, then you can still do it. And at least asymptotically, you can guarantee that your variation estimate will deliver the right. So I'll stop here and maybe pause for some questions before I go on to the algorithmic side.
So how much of this is coming down to the choice of variational family as much as maybe objections to what KL is metrized?
Sure.
Yeah, like if you're caring about point estimates, presumably that's the mean or the median.
Yeah.
And KL doesn't capture closeness. So how much of that is that phenomenon? How much of it is for choices of the variational family?
Right. I mean, so if I understand your question correctly, so you're asking, I mean, if we actually replace this one by some other metric, which is probably metrizing the correct distance between the statistical model, probably yes, but then since we are dealing with likelihood ratios, KL comes up naturally.
Okay.
But yeah, it's a good point. And if you're dealing with dense things which are not densities, for instance, like generalized densities, something like that, then probably something else would come. Okay, so let's move on to the algorithmic side of things. For this part, I'm going to restrict ourselves to the mean field inference. So we assume that there are m parameters which are grouped into d many variables, and each block size is mj. And we assume a mean field on these blocks. And as we discussed a while ago, you can actually do coordinate ascent, meaning that you can update one variable at a time, fixing the other variable. And in that case, the problems are convex, and you can write down the explicit form for the updates. So you can actually look at exponential family models, and in those cases, the updates are analytically tractable, and you can study convergence, but we want to have a general framework for convergence of this algorithm. Now, let's look at two versions of the coordinate ascent algorithm. So depending on how you update the individual coordinates, so you can either choose to update Q1 and Q2 at time point t to Q1 and Q2 at time point t plus 1 globally, right? Or you can choose to update them sequentially, meaning that you update Q2 given Q1 and update Q1 again based on the most recent value of Q2. Okay? So we're going to call the first one as the parallel dynamics and the second one as the sequential dynamics. And let's see how these two algorithms behave in a very simple example of linear regression. So we have 100 samples, 100 variables, sparsity is 20, covariates are Gaussian, noise sigma square is 1, errors are Gaussian as well. And the first 20 betas are set to 1, the remainder set to 0. In this particular example, the SNR is quite high, so it's a detectable range, so there is no issues there. And you run a coordinate ascent with the sequential version first, and then you run the parallel version first. Okay? let's look at the results for the sequential update first. So the red dots are the variational estimates, and the black dots here are the true values of the regression coefficients. They kind of align pretty nicely. The evidence lower bound is nice increasing, and it stabilizes after 20 iterations. So things are quite well behaved here. Now, I do not have a picture for the parallel version because things completely collapse. The elbow actually diverges to negative infinity.
I mean, would the picture look qualitatively the same if I just took X to be identity, in which case, I guess your whatever factorization.
Sure, yeah.
So it would be
yeah.
I mean, I'm just trying to understand, like, roughly my high level question is how sensitive is any of this to the conditioning of X? Like, if it was really nasty, it must have been really nasty.
Of course, yeah.
And so but for a kind of random matrix like that, it's not identity, but it's probably not too terrible.
Yeah. So definitely the conditioning plays a huge role. So if let's say columns of X matrix are nearly correlated, then none of the algorithm will deliver the right thing. And it would depend a lot on the initialization. You have to initialize very close to the true. Okay, so how to actually make sense of all of this? One thing you can do, and what the literature is actually doing, is to write down dynamical systems for the two algorithms, and you simply analyze the stability of the dynamical system, but this is really too case specific. So what we found out is when you're updating using coordinate ascent, convergence is roughly inversely related to how much information is propagated between the two blocks, let's say in the two block case. And this information is actually given by this delta n, which is the integral of Q1 minus the optimized value times Q2 minus optimized value integrated with respect to the log posterior distribution. Now let's try to understand this quantity a little better. So since delta is itself unbounded, we tried to normalize this delta by dividing them by the symmetrized scale divergence between Q1 and Q1 star, Q2 and Q2 star. In that case, it looks like a correlation kind of quantity. We call it the generalized correlation. And what we found out is that if the generalized correlation is between 0 and 2, then both the parallel and the sequential coordinate ascent will globally contract. Note that this is just in the d equals 2 case, which is different from the regression example I just showed. Now you can make this more formal. In particular, if you have the generalized correlation between 0 and 2, then it's actually a contraction, meaning that the KL divergence between Qt plus 1 and Q star would be less than or equal to some number between 0 and 1 of the KL divergence in the previous iterate and Q star. And this constant kappa n is actually related to the generalized correlation. So it's actually strictly between 0 and 1. Now, just to illustrate the idea for the very simple Gaussian model with correlation matrix, with precision matrix n times q, which is often encountered in Bayesian problems, what we have seen is that the generalized correlation is actually 2 times the partial correlation between the two blocks, which is guaranteed to be less than 2. So if you run this for a Gaussian example, then no issues there. So as a byproduct of this condition, one can actually show that your Q star is the unique global minima of your objective function. But this global bound on the correlation may not always hold. It holds for a simple example like the Gaussian. So we need to formulate a local version of the result. So how do you formulate a local version? So instead of taking suprema over all densities, we simply take suprema over certain neighborhood around the two parameters. Okay. So we still have the correlation quantity, and then we take the suprema over certain neighborhood, which depends on R naught. And there is a typo here, it should be pi n R naught. So the local version of correlation come here. And then you will have the exact same version for the global version, which is saying that if you initialize within this particular neighborhood, then you have a contraction. Okay. So now this is not exactly useful for a practitioner because you don't know what Q star is. But at least you know for some examples where you really need the local condition, initialization is really important in those examples. And that's what we kind of did. We actually ran through a lot of examples, and we found out that we, in problems where there are no latent variables, we actually have a global condition on the target. But if in problems where you have lots of latent variables like mixture models, exponential family latent variable models, Ising models, then you need the local version of the correlation condition. So these are only for two blocks. So we are still not yet, we have still not yet settled the dichotomy between parallel and the sequential version in the regression case. That would be possible if you have an extension to the general D case, okay? So you can naturally extend the idea to the general D case by defining local versions of this correlation between the jth block and the remaining blocks, and then taking maximum over all possible variables. And now what we can prove that the results extend only to the parallel case for general D if the generalized correlation is less than 2 over square root D minus 1. Now, of course, the question is whether this bound is tight enough. And we have an example to show that it's actually tight. So if you look at target Gaussian matrix with target Gaussian distribution with precision matrix given by this compound symmetry structure, then the fact that generalized correlation is less than 2 over square root D minus 1 is equivalent to having the absolute value of rho less than 1 over D minus 1. Of course, you can't have rho to be very close to 1 because of positive definiteness, but this tells you that for the parallel version to contract, you can't have rho to be too positive. Okay? And you can analyze the dynamical system itself, and you can take the spectral radius, and in that case, you can show that the parallel converges if and only if the absolute value rho is less than 1 over D minus 1. So there is really no gap between what we are delivering here and the actual scenario. Now, what happens to the sequential version? You can actually show that the sequential converges for all rho values. And we are kind of like little puzzled by this phenomenon, but this is nothing but the Jacobi iteration and Gauss-Seidel. And Gauss-Seidel is the sequential version, which doesn't need any condition to converge in this particular example. But Jacobi iteration needs diagonal dominance, and this diagonal dominance actually translate into this rho being absolute value of rho being strictly less than 1 over D. Now, going back to the regression example, we can show that under Gaussian design, again, we are not looking at correlated design that brings up another can of worms, but at least under Gaussian design, if the sparsity square is small o of the sample size, then the parallel version will contract. And if you go back to the example, so we need sparsity squared to be small o of the sample size, which is not met here. right? And that's the reason the parallel version will not converge. For sequential version under IID design, you don't really need any condition. Very less restrictive conditions in order for this algorithm, sequential version of the algorithm to converge. Okay, so so now you can actually tie up the statistical and computational guarantees by this like master theorem. So what we can show is if your variational optimizer is delivering minimax risk, and if you initialize your algorithm within certain neighborhood of the true parameter, then at the kth iteration, the variational risk is bounded by the minimax risk. If you choose the number of iterations to be scaling at a certain rate, depending on your contraction number here. So that's pretty much it. In terms of recommendation, you have to be careful in latent variable model if you're using sequential algorithm. It depends a lot on the initial. So unlike the common folklore that you should block variables in order to improve your mixing for MCMC, this doesn't really hold for variational inference. Try to avoid parallel coordinate ascent if you have lots of variables. It also tends to have some cyclical behavior that we have observed in the case of Ising models, and it has very small radius of convergence in the sense that you need sparsity squared to be of small of n, which is typically a more restrictive condition. So of course, this is all for the mean field, at least the computational side of things. We currently don't have any guarantees beyond mean field, and that's what we are working on at the moment. So this is a joint work with a couple of students. Sean is now a faculty at the University of Arkansas. Honggang is a final year student at A&M, and my colleagues Anirban at A&M and Yoon, who is currently at Maryland. So I talked about these 4 papers, which are in red. So there are other variational inference works that I have done. So that's in blue in case you're interested. And that's it. And thanks for your time.
Thank you, Debdeep. We have a couple minutes for questions if there are any. If not, thanks Debdeep again, and thank you all for coming.